2005 bi-monthly SIPN webinar series, which is organized by Muyin Wang, who is also a member of the SIPN leadership team. Muyin is a research scientist at NOAA and the Joint Institute for the Study of Atmosphere at the University of Washington. Muyin, at this point, I'll turn the program over to you. Muyin?
Thank you, Betsy.
Thank you.
It's my pleasure to introduce. Can you see? Okay. All right. Thanks, Betsy. It's really my pleasure to introduce our speaker today, Dr. Elizabeth Hunke. Elizabeth is a primary developer of the Los Alamos CICE model, CICE, which pronounced as CICE, which is used in numerous operational and climate modeling centers around the world, including the U.S. Navy, the UK Met Office, Hadley Center, and the NCAR DOE Community Earth System Model, as well as modeling centers in Australia and China. And in a recent study, we found out that among the 12 better performed CIMA-5 models, half of them actually use the CICE for their CICE component. So CICE was developed for global climate studies on highly parallel computing system, but it is also used for smaller scale, higher resolution studies of regional climate processes. So at Los Alamos, Elizabeth is a member of the Climate, Ocean, and CICE modeling team and works within the Fluid Dynamics and Solid Mechanics group in the theoretical division. Elizabeth serves as a U.S. delegate to the International Arctic Science Committee Cryosphere Working Group on behalf of the National Academies of the Science Polar Research Board. Although she spends most of her time working in front of the computer in New Mexico's high desert, Elizabeth has enjoyed CICE and oceanographic field experience in the Wild Sea Antarctic. Now let's welcome Elizabeth to give us her talk.
Okay, hello everyone, and thanks for joining us today. I'm going to provide a general survey of the CICE model features and advances, motivated from the point of view of the radiation budget.
Excuse me, Elizabeth?
Yes?
This is Judy. Can you please share your desktop?
Oh, let me see if I can figure out how to do that. I thought I was sharing it. Let's see. Ah, there it is. Okay.
Yep.
Did that work?
Yes.
Great, thank you.
Okay, let me get back to my full screen mode. Okay, so as I said, I'm going to try and motivate this from the point of view of the radiation budget in the CICE. And so first, I'll try to give you some background on the major components of any CICE model, and then describe how various factors in the radiation budget are modeled. I won't get into the technical details here, but I'll try to give you an idea of what the current models are capable of. So I'll begin with some general background for audience members who may be new to this topic. First, sea ice is frozen seawater. That's different from land ice like glaciers and ice sheets because they are made out of snow that is compacted into ice. But sea ice is frozen ocean. And there are many scales at which one can consider sea ice, from the micro scale of individual crystals to the scale of individual blocks of ice, to the flow scale, to the basin scale. In the global climate models, we are mainly concerned with the basin scale, but we can and do include scales down to about 10 kilometers or less. We try to include the smaller scale processes in a parameterized way, modeling them in terms of the larger scale variables. Now, sea ice is an enormous factor in the climate because ice covers a large area of the Earth. Here, I'm showing the sea ice extent for 1988 in white, and the pink line is the long-term average for 1979 through 2000. So this does not include the more recent ice losses. The top pictures are looking down at the Earth at the North Pole from above, in the winter, which is February in the Arctic, the ice extends a long way south and covers a huge area. But by September, which is the end of the summer, the ice has melted back a ways, but it still covers a pretty large area. And then the seasonal cycle in the Antarctic is even larger, with nearly all the ice melting away in summer. So sea ice covers about 4% of the Earth's surface, but it accounts for perhaps 8% of the planet's total reflected energy. And so it contributes significantly to the balance between the energy delivered to Earth as sunlight and the energy radiated from Earth's surface as heat. This plot shows the total Arctic ice extent in September from 1979 through 2014, the length of the satellite record. 2007 and 2012 were unusual years, but there is a lot of variability from year to year. And the trend is toward less ice in the summertime. This is a similar plot for the Antarctic, and here the trend is going the other way toward more ice, although the interannual variability is huge. Last month we saw the highest January Antarctic, or actually it was in January, not last month, this is March. We saw the highest January Antarctic sea ice extent on record. We don't understand what's driving these changes in the Antarctic, but last month, or in January, the increase in sea ice extent seemed to be caused by stronger winds from the south, expanding the ice northward. As the ice becomes more expansive in the south and melts back in the Arctic summer, the global radiation balance is changing. Though sea ice has extent, it also has thickness, but its vertical thickness is much smaller than its horizontal extent. Young, undeformed ice is generally 1 or 2 meters thick at most, but sea ice is often deformed into ridges, like you see here, usually less than 10 meters thick. And that's Steve Ackley out on the ice in the Weddell Sea. Okay, so in addition to being three-dimensional, the sea ice is also in motion. This is a video of sea ice near Svalbard. And we do not try to model the motion of individual ice flows, but we do try to capture the larger scale patterns of ice motion across the basin, as in the upper illustration. And as it drifts around on the surface of the ocean, the sea ice carries things with it, pollutants and dust, for instance, which can affect the ocean ecosystem when the ice melts. And the ice is not pure ice. It has a lot of stuff in it, mostly taken up from the ocean as the ice freezes. This photo shows a layer of algae that has grown within the ice. As you might imagine, the relatively dark-colored algae absorbs sunlight and warms the ice interior, thereby contributing to ice melting and disintegration. The sea ice ecosystem has motivated a lot of our recent model development work, which I'll mention later. Okay, so this is an example of a simulation using the sea ice model in standalone mode. That is not coupled to models for the other climate components like the atmosphere. This shows the ice thickness in color. The red line around the edge is the observed 15% ice concentration contour, and the white line is the 15% ice concentration from the model. Since the sea ice model is run uncoupled, I have to feed it some sort of data to represent the other climate components, such as the wind, the air temperature, ocean currents, and so on. In this case, only 3 fields vary from year to year: the wind, the temperature, and the humidity. All the other forcing fields are climatologies, which mean they have the exact same seasonal cycle every year, or else they are computed from the other fields. This simulation does pretty well because it includes the most important processes, namely the wind stress on the ice, the albedo feedback on the sea surface temperature, or SST, and my 50-year run also has a long-term thinning trend, which is very important for preconditioning the ice to melt. So let's talk about what's in the model. Go back one. I looked for a fancy illustration of the sea ice thermodynamic model online, and I didn't find one. So this is the original schematic from Makut and Untersteiner's 1971 thermodynamics paper. And if you'll note from the caption at the bottom, this was their entire sea ice model. Models have become a lot more complex since then, as we will see, but this is the foundation on which our modern models are built. So the schematic shows air at the top, which is over snow, which is on top of a layer of ice, and that in turn is floating in the ocean. The arrows at the top represent the fluxes between the atmosphere and the snow or ice, and they determine the temperature of the snow or ice. The terms inside the snow and ice represent heat conduction through the material, and that is the basic thermodynamic model here, the heat equation with an internal heat source from radiation that penetrates below the surface. So that's the equation that I've written on this slide. One essential aspect of sea ice thermodynamics is the variation of the growth and melting rates for different ice thicknesses. This is just a cartoon, but it illustrates that when the ice is thin, as it is over here on the left, it grows and melts very quickly because the rate goes like the vertical derivative of the temperature. Now, in global climate models, grid cells are pretty large, usually a few to around 40 kilometers on a side. So we try to capture the variation in the thermodynamic growth and melt rates by dividing the ice in each grid cell into thickness categories, or what we call an ice thickness distribution. So theoretically, this is a distribution in the mathematical sense, but in practice, we just have a few categories, typically between 5 and 20. We do have more of them in the thinner ice range to better resolve the growth rates there. Now, we track both the thickness and the area fraction or concentration of each category, and so the ice thickness distribution essentially increases our resolution for the thermodynamics. This cartoon illustrates our typical ice thickness distribution configuration. There are 5 categories, each with several vertical levels in the ice and some snow on top of it, and each category has its own thermodynamic flux balance. In mathematical terms, the ice thickness distribution is an area. It's the fractional area of the grid covered by ice in a given thickness range. So this equation describes the evolution of the ice thickness distribution, and it is the fundamental equation in the sea ice model that ties together all of the various processes. So, for instance, the ice thickness distribution changes due to thermodynamic growth and melting in red, and also due to dynamic influences, namely the convergence and divergence of the ice and mechanical redistribution or ridging processes. So if you were to ask yourself what aspect of sea ice is most important, your answer would likely depend on what physical question you're interested in. So if you're an oil company, then you're probably interested in the ice mechanical properties. If you're a biologist, you're probably more interested in the chemical and hydrological properties of the ice. But for a climate modeler, it is the albedo, or the reflectivity of the ice. This is a photo of the summer ice pack in the Antarctic, and you can see that it's not a solid cover. We model the ice area coverage here as an ice fraction or concentration that's uniformly distributed over a grid box. In the wintertime, it's nearly 100% or completely white. But at other times of the year, the ice cracks and melts, and the ocean begins to show through. This contrast between the white ice, which reflects sunlight back to space, and the dark ocean, which absorbs the sunlight and becomes warmer, that contrast is the most important aspect of sea ice in the climate system. When it's there, the sea ice prevents the ocean from getting warmer, and when it's not there, the ocean gets warmer and melts back the ice even further. So this is a feedback loop. But this feedback loop also works the other way. It's a little cooler. If it's a little cooler and more ice forms, that can reflect more sunlight, causing more cooling. So sea ice tends to enhance the changes in whatever direction they're already going. Now let's come back to the radiation budget. Here I've circled the 2 major pieces, which are the long wave and the short wave for solar radiation. The numbers here are from Makut-Untersteiner's paper, and I want to point out that the net flux, adding all of these together, is a relatively small number compared with the magnitude of the fluxes themselves. So the net flux is about 40 watts per square meter, while the individual fluxes are more like 300 watts per square meter. The albedo is alpha in the reflected shortwave vector. A relatively small change in the albedo, 10%, for instance, could reduce the reflected shortwave by about 24 watts per square meter in this case, but that's over half of the net flux, which is only 40 watts per square meter. So very small changes in the radiation balance can have very large influence on the overall heat balance in the ice. Now, clearly, the area covered by the ice itself is important because of the different albedos of ice and ocean. In the model, the primary processes that determine the ice area are the lateral growth and melt rates at the flow edges and the ice motion. We model the ice motion using a constitutive equation, or a rheology, that describes the material properties of the ice, such as how much force is required to make it deform. There is a momentum equation that incorporates the internal stress from the constitutive equation, along with external forcing like winds and ocean currents. Then there is a set of transport equations that ensure conservation of ice area, volume, energy, and related quantities as the ice moves horizontally over the ocean surface. Recent improvements to the ice dynamics have been contributed by Danny Feltham's group at the University of Reading in the UK. They implemented an anisotropic rheology for the model, which assumes that when the ice fractures, it does so in preferred directions. They also implemented form drag into the model, which alters the drag coefficients based on the roughness of the ice. So instead of using constant drag coefficients everywhere, the drag coefficients depend on the ridges and keels of deformed ice and also on the ice edges. There's a flow size assumption based on the ice concentration, and melt ponds also have edges that contribute to the ice roughness and alter the drag coefficients. So here's an example using the form drag parameterization. The control run is on the top with the form drag turned off. It's turned on in the lower plots, and in that case, the thicker ice near Greenland is more heavily ridged. So the drag coefficients there are larger, and that ice moves around the Beaufort Gyre toward Alaska. This is not obvious in the ice thickness plots on the left, but that change kind of jumps out in the ice age diagnostic that's in the middle. The ice age also shows younger ice over the North Pole and a blob of 3 to 4-year-old ice in the Central Arctic Basin, which is pretty similar to the observations that we see on the lower right. So the location of the ice, its area and its extent, is the single most important factor for describing the radiation budget in the sea ice model. The amount of snow on top of that ice is also critical because snow is highly reflective. And we do model the thermodynamic effects of snow, again using a vertical description of conduction through the snow that depends on the fluxes at the surface and at the snow-ice interface. We assume a density profile, which at the moment is constant, although we're working on that. And because snow is highly heterogeneous, we use an effective thermal conductivity for it. We also assume that the snow is fresh unless it's been flooded by seawater, in which case it turns into snow ice. Other snow mass changes are due to precipitation, sublimation, or deposition of water vapor, melting, and there's some loss of snow into the ocean when the sea ice ridges. Snow is transported on top of the ice as the ice moves across the ocean surface, and the snow interacts with melt ponds on the ice, which I'll talk about in the next slide. So the snow model is a primary focus of development in the sea ice model right now. We will allow the snow to be blown around by the wind, and we will allow the snow grains themselves to evolve into depth hoar, which has very different radiative characteristics than fresh snow. And eventually, we will allow its density to evolve with time, too. So melt ponds are pools of liquid water that from snow or ice melt on top of the ice. And they are relatively dark in color, and therefore they can accelerate the ice melt. They form in low spots, and if there's enough snow, they may not be visible until the snow becomes saturated. They can drain through to the ocean when the ice becomes warm and permeable, and if it's cold, they will refreeze on top. Then, if it snows, the snow collects on that ice and hides the ponds again. And like snow, ponds are transported horizontally on the top of the sea ice. So the model has represented melt ponds in some form for many years now, but in the new version of the sea ice model, we added 2 more schemes that do all of these things in great detail. The primary difference between the 2 new parameterizations is in how they determine where the ponds are located on the sea ice. Ice thickness also has a very strong influence on the albedo, particularly for the thinnest ice types. As you can see here, when the ice is very thin, it's mostly transparent, sort of like an ice cube. Sunlight goes straight through it into the ocean and then melts the ice completely. And if I tried to include everything that affects ice thickness, I'd have the entire model written on this slide, because thickness is the time-integrated result of everything that goes on in the model. But the processes that directly alter thickness include mechanical deformation, where the ice is converging with enough force that it crumples up into ridges, and thermodynamic growth and melt. There is melting at the top and the bottom of the ice and freezing at the bottom. Fragile ice grows mainly in the open ocean between ice flows, but it does contribute to the overall ice thickness. And flooding causes snow to be converted into ice, also thickening it. In Sea Ice version 5, we've added an entirely new thermodynamic model that treats the sea ice as a mushy layer, which is a mixture of brine and solid ice. As part of that, we improved the snow ice representation to account for the seawater that floods and saturates the snow, instead of it being simply an isostatic balance of the ice and snow floating in the ocean. The ice itself is quite heterogeneous. Starting at the bottom, ice crystals grow out of the seawater, and as they grow, the seawater or brine is captured among the crystals, and that alters the conductivity of the sea ice. Now, this plot is from a 2-dimensional model simulation by Ortling and Watts that simulates what happens as the ice grows. The ice layer in the middle is cold at the top and warm at the bottom, which should cause convection all by itself. But in addition, as the pure ice crystals form out of the brine, they leave even saltier brine behind, which is heavy. So the brine tends to flow out the bottom of the ice, while less saline seawater flows in through the bottom of the ice. Then, when the ice becomes very cold, the brine that's left in the ice structure forms brine pockets. This is an X-ray tomography image of sea ice showing the brine pockets in yellow. Then, when the ice warms again, the brine pockets expand and interconnect, creating brine channels. Now, the brine channel network can be fairly large scale, as seen in these photos of ice slices. And we're seeing both horizontal ones here and vertical ones on the right. The melt ponds can drain through the brine channels when the ice becomes warm and permeable. And this freshwater fluxing can clean the ice quite effectively of salt, nutrients, and other inclusions. So our approach in the model is to treat the ice as a mushy layer, which, as I said, is a mixture of brine and solid ice. The core of the mushy thermal model consists of 4 equations that represent 4 physical properties: conservation of energy in salt, the relation that describes the fraction of the mush that is solid or liquid, and a description of the flow of brine through the ice matrix. So far, I've been talking about the processes that affect the radiation balance without talking about the radiation itself. So for that, we use a multiple scattering parameterization in which incoming solar radiation bounces off different layers within the ice and snow, getting absorbed as heat as it goes. Eventually, a small amount of radiation may exit the bottom of the ice into the ocean, particularly if the ice is thin. The ice may have snow on it, or it may be bare, or it may have a pond on it, or some combination of all 3. This radiation calculation is done for each surface type, snow, ponds, or bare ice, and for each thickness category. So if we have 5 thickness categories, we can have up to 15 radiation calculations in a grid cell just over the sea ice. So we assume that the very thin snow is patchy, so it doesn't cover the entire area of the ice. And we use parameter values that are based on measurements for basic or inherent optical properties, such as the extinction coefficient, single scattering albedo, and the asymmetry parameter for the scattering. From these, we compute the apparent optical properties that are used in the sea ice thermodynamic model, such as the albedo, the internal absorption, and radiation that's transmitted to the ocean. This very detailed parameterization is based on fundamental physics, and so our tuning parameters are things like the snow grain radii, of which there are several different kinds. A big thrust for climate modeling right now is the biogeochemistry, or ecosystem modeling. It involves a very tight coupling between the sea ice physics and the chemistry and biology that resides inside the brine pockets. As I mentioned earlier, this is driving many of our model development choices for the sea ice model. And I want to show you an example that combines some of the concepts I've mentioned so far. We've been collaborating with researchers at the International Arctic Research Center in Fairbanks to develop an ecosystem model that simulates nitrate, silicate, ammonium, and dimethyl sulfide, or DMS, in the ice, and which is closely coupled to our ocean model and its ecosystem. This figure shows the progression of an algal bloom in the bottom of the ice in the Arctic. On the x-axis are the months, January through December, and the y-axis is latitude. So the bloom begins at lower latitudes in the late winter where there is some light, and it progresses northward with the sun. The lower edge of colors is the ice edge retreating northward. In the summer months, the ice melts at the bottom, causing the algae to be flushed out into the ocean. And then in the fall, when the ice begins to freeze again, nutrients are taken up into the ice and the algae show a secondary bloom. We've also implemented aerosol chemistry in the model, where dust and soot land on the sea ice and then pass vertically through the ice with growth and melt, and by flushing of the meltwater. These aerosols affect the radiative transfer in the ice, and the results shown here are from an earlier version of sea ice run in the CESM, Community Earth System model, showing the increase in shortwave absorption due just to aerosols in June and July on the left and right, for a pre-industrial scenario on the top, which is labeled one-time CO2 here with 285 parts per million by volume of CO2, and for a second run with twice as much CO2 forcing shown on the bottom. We find that in the warmer climate, there is more ice melt. The ice is warmer and more permeable, and therefore more of the aerosols are flushed out of the ice, resulting in less shortwave absorption due to aerosols than in the pre-industrial case. This will also be true for other biogeochemical tracers, and it will be interesting to see how the salinity of the ice pack changes as a result of these sorts of processes as the Arctic warms. Salinity does have a large effect on the ice conductivity and therefore the growth and melt rates. Changes associated with the ecosystem can feed back on the physical climate system. One of the major model advances that we're working on now is a full vertical description of biogeochemistry in the sea ice. This simulation is in the southern hemisphere, where algae blooms at the snow ice interface, shown as the pink line. The interface is slightly below sea level and therefore flooded with seawater for a few weeks. When the algae use up all the nutrients there, the bloom fades, but then another bloom occurs later at the bottom of the ice as the irradiation increases. And finally, I would be remiss not to mention clouds, although they're not modeled in the sea ice component. They are part of the atmosphere models, but they have a huge effect on sea ice because they reflect sunlight, they emit long-wave radiation that warms the ice, they act as a blanket over the lower atmosphere, and they provide precipitation, which is utterly critical in the sea ice radiation budget. Fortunately, they are someone else's job to model, but their effects are incorporated into the sea ice model. So to summarize, sea ice models have become a lot more capable, and they've incorporated many more processes over decades. The basic processes such as ice deformation and motion and the basic thermodynamic description have been around for a long time, and these are very well represented in the models. However, modelers still have much to do to improve the models, particularly as new questions are being asked of them. So, for instance, many questions being asked now revolve around the biogeochemistry of the Earth system. How does the sea ice ecosystem interact with and alter the ocean system? How does it contribute to the aerosols that become cloud condensation nuclei? With the older models, we could not have answered these questions because we could not cycle chemical or biological constituents through the snow and ice in a physically defensible way. So these kinds of questions are now motivating our sea ice model development work. And that's all I have. I'd be happy to take questions.
Okay.
Is important from the ecological point of view. Yes. Yes. Thank you very much, Elizabeth. This is Judy. It looks like Cecilia Vitz has a question. Go right ahead, Cecilia. You'll need to unmute yourself. Cecilia, we should be able to hear you now. I show that Cecilia is not muted, so I'm not sure. Maybe she's muted her microphone or something somewhere else. We have another question from Siri Joda Kalsa. What aspects of the model are most sensitive to the horizontal scale that is chosen to run the model on?
That's a very good question. The horizontal scale of the model mainly comes in through the dynamical aspects of the model. The thermodynamics is all vertical. And so we do have to make some assumptions in the thermodynamics about the heterogeneity or homogeneity of the grid cell. But in the dynamics, the scale comes in because the ice is moving and being transported. And because the sea ice is a more or less solid material, it has these constitutive properties where it can crack, and how it moves depends on how that cracking happens, and the horizontal scale comes into that part of the model.
Hi, this is Betsy in Fairbanks. Cecilia, maybe your phone is muted as well. I see that she has her hand raised, so let me see if I can find her chat.
This is Judy. She sent in a question and comment. Great talk. When do you think the winds on the short term hand over the dominant control to the radiation on the longer term? How does the answer relate to prediction?
I think Cecilia can probably answer that question better than I can. Goodness. Well, the winds are primarily acting on a on a synoptic timescale, they certainly affect the long-term evolution of the ice pack, where it's going, where it ends up. And we see that on the seasonal scales, especially in these anomalous years where we have either too much ice or too little ice. In terms of the radiation, I don't know. I think they are both very important, but my feeling is that the winds are more important on the short time scales than the radiation is on the longer time scale, like for the whole season. But as we model clouds better, the answer to that may change.
So I have a question.
Go ahead.
So based on your scheme, so the ice growth and retreat have a two scheme. One is two processes. One is thermodynamic, the other is dynamic. Is there easy way for you to can distinguish the two processes? I mean, how much the ice grows due to the thermodynamic and how much due to the dynamic process?
Yes, we can do that in the model. It's much easier in the model than it is in the real world, because since we're doing all of those calculations individually in the model, we can just keep track of, you know, this change in the volume occurred because of this thermodynamic process, and this change in the volume occurred because of the dynamics. So we just track that in variables.
So do you have idea what's the percentage of each?
It varies with the season.
Okay.
Yeah. I can't give you numbers right off the top of my head, but in general, what you see when you're comparing those variables, the thermodynamic ones versus the dynamic ones, is that you'll see an increase in ice in a particular area of the Arctic because the dynamics, say the wind is blowing it over there, and that means it's leaving some other area. But in that area that it leaves, then the thermodynamic variable will show you that new ice is growing because you've opened up some space there, so the open water. And so those two variables show how the two kinds of processes kind of go back and forth between them.
Okay. Thanks.
Hi, this is Betsy. I'm wondering if there are any other questions. I see that a few people have their phone unmiked as if they might want to be asking some questions. Any other follow-ups to the presentation?
This is Judy. Cecilia chatted that there is excitement about Earth system prediction on sub-seasonal to seasonal timescales. Do you think biogeochemistry in sea ice models is ready to be used?
I think it's getting close. It's not, well, let me be a little careful about what I'm saying here. There is already basic biogeochemistry in the sea ice models that is being used. For instance, the aerosol plots that I showed you before. What we're working on now is getting those effects in the sea ice fully coupled to the rest of the system so that, for instance, what happens in the sea ice can actually affect the cloud condensation nuclei. That work is being done right now, and so I think it'll be ready to go here very shortly. And then the full biogeochemistry, the full vertical biogeochemistry that I showed toward the end, that's still in the development work. right now, and we'll be testing it in some local kind of standalone sea ice configurations, but it should be ready to start being used in coupled models, I would say, within the next year or so. So we are getting pretty close with that. And I see Stephen Ackley has his hand up.
And Judy, can you either read his chat or unmute him?
He is not muted. He should be able to speak.
Okay. Steve, would you like to ask the question, or Judy, are you seeing any kind of message from him?
No, I am not.
Okay.
Steve, if you are having problems, we're having problems hearing you. So if you want, now you're muted, I see. You just muted yourself, and now you're unmuted. So if you are having problems or we can't hear you, you're welcome to use the chat window to ask your question.
This is Ulla Person. Can you hear me?
Yeah.
Yeah.
I had a question for Elizabeth. I was curious whether the proportion of surface melt versus bottom melt is realistic in the model, in the implementations of the model as she's seen them.
The proportion varies a little bit depending on the forcing that you're using. There are some, yeah. I think in the coupled models, well, I'm not the best one to answer that because I don't know the results from the coupled models all that well. But I think they're reasonable in the coupled models. I know in my standalone configuration, the radiation fields that I use are a little bit too strong, and so I tend to have too much surface melt.
Yeah.
So that's just something we have to pay attention to when we're looking at the results.
Yeah, I've seen some of Don Pervich's results measurements and suggest that somewhere between 25 and 75 for the top and the bottom. And I was curious if you had if the model was producing similar type of results.
Yeah, I think it's similar. I should contact Don and get that data so I can compare it.
Yeah. All right, thank you.
I think we've got several minutes left here, so if people want to ask questions just by stepping in as it's been going, that's just fine. That's a good way to go.
Elizabeth, this is Judy. There's also a text from Jennifer Francis. She says, in terms of seasonal sea ice prediction, what do you think is the most important known unknown?
I think we don't have a very good handle on the snow in general and everything that has to do with the snow, including the amount of precipitation and how it's going to change. That's my very general answer.
Stephen Ackley asks, any plans to incorporate waves into ice formation and tides into ice deformation?
Okay. There is some work being done on that by other groups, but they're doing it within my model, the sea ice model. So I expect I'll get that back at some point. They are looking at how waves break up the ice around the edges. And as far as tides, there's been some work on that, but I don't know whether there's anyone specifically working on it right now. I have a question.
We have another question. Sorry.
Okay, this is Elizabeth. I have another question that Martin Jeffries wrote, and he asked, how much priority would you give to improving the treatment of top and bottom roughness in the model? What sort of improvements are needed? For that, the form drag that I talked about earlier in the talk was really about that. We aren't trying to change or tune the roughness parameter, but rather add in some of the processes that affect the effective roughness in the model. And what's been done is a great start. I think there's still some improvement that can be done to that parameterization, and we have some ideas for what to do with that now, so maybe that'll happen in the next short while. In terms of priority, well, it's hard to prioritize. There's a lot of different things that need to be done in the model to make it better, and that's one of them. But you may have gotten the message from what I've said so far, is that to me, snow is the top of the list right now, and the other things fall below that.
There was another question that came in from Hongji, and they say, Liz, what is the recent model performance in the Antarctic sea ice?
Model performance, as in how well is it simulating what the Antarctic is doing? I don't know. I haven't run it for the recent years because my forcing data that I use goes out to 2009. So I haven't run it for the more recent years where we're seeing the big increases in the Antarctic ice extent. I don't know whether anybody else has run it out there. If they're on the line, they can speak up.
Are there any other questions that are being asked on the, it looks like people are using the question and answer function, which is available in addition to the chat function. Please, if you're not being answered or not being acknowledged, please just speak up into the phone.
We have one more question from Thierry Joda Kalsa. How many implementations of CICE are you aware of?
Oh, you mean how many people are using it?
Well, I can help with that. So we looked at the 37 CMIP5 models, and 12 of them using the CICE.
Yeah, that's in the CMIP5 models. There's also a lot of people that are using it who aren't contributing to CMIP. So
right.
There's, it's being used operationally in 1 or 2 places. I don't have the website handy, but I have been keeping a website listing of all the users, and I think I had somewhere between I want to say 50 and 100 users in 18 countries or something like that. It really has been a very successful model.
I see a comment from Cecilia. She says the physics are appropriate for the Antarctic, and it looks quite good in CESM CAM 5.
Oh, good. Thanks, Cece.
Okay, any more questions?
It looks like not. It looks like it might be time for us to conclude the webinar. If there are any other questions, this is your opportunity. Otherwise, please go ahead. Somebody? Nope. Then please go ahead and contact either Elizabeth or Muyin via email or contact me, Betsy Turner Bogren at ARCUS, and it's just betsy@arcus.org. This event will be archived and online later in the week, and we will send an email to everybody that registered to let them know that it is archived and available. One more time, I'd like to thank Elizabeth Hunke for sharing her expertise with us and for everybody that participated and helped set up the webinar, and to Muyin Wang and the rest of the SIPN leadership team for organizing the webinar. And we will announce future events in this webinar series shortly, so stay tuned to the SIPN list and also to the ARCUS list for notification about those. Thank you very much for participating, and we'll conclude today's webinar at this point. Thank you.
Thank you, Betsy. Thank you.
Thank you.